Bismillah Rahman Rahim. So today we are starting the lecture with some useful quantities that we used during the mechanical vibration. Uh, Normally, when the vibration is sinusoidal or periodic, then more of the time we are concerned about the amplitude A and the frequency at which the vibration is taking place. Up till now, you have studied that if we have free vibration, so in that case, the system would vibrate at the natural frequency. So capital A, normally last time we discussed that x of t, which is actually the displacement of the vibration or response of the system, we could mathematically model it as x of t is equal to a sine omega nt plus phi, or x of t is equal to a cos omega nt plus phi, where a is actually the amplitude of the vibration, or it is also known as the peak value. So it is the peak vibration. When the vibration is not sinusoidal, it is random, then in case of a random vibration, because we know that the displacement is a random number and also the frequency is a random number, so it changes with the passage of time as vibration takes place, depending upon the nature of the vibration, whether the random vibration is narrow band random vibration or broadband random vibration. So in case of random vibration, we are more concerned about the average value of the displacement and how to compute the average value. It is denoted by x bar, and mathematically it is equal to limit time period tends to infinity 1 hour time period integral 0 to t x of t dt. So with that, we have to compute the average value of the displacement. And how to calculate the mean square value? It is denoted by x bar square, and it is equal to limit t tends to infinity 1 hour t integral 0 to t x square of t dt. And another important parameter that we normally consider during the random vibration is the root mean square value. It is noted by x RMS value, and it is actually equal to the square root of the mean square value x bar square. So in case of random vibration, we normally are more interested in the average value of the vibration or displacement, mean square value of the displacement, or root mean square of the displacement. However, in case of sinusoidal vibration, more of the time would be talking about the amplitude and the frequency of the vibration. Similarly, also likewise, displacement has a peak value, which is the amplitude of the displacement. X maximum is equal to capital A. Similarly, we also discussed that the velocity has the amplitude. The system is vibrating, the mass is vibrating, it is moving with displacement x. So at the extreme positions, the displacement would be maximum. However, at the equilibrium positions or at the mean position, the displacement would be zero. However, at the mean position or equilibrium position, the velocity would be maximum, and x dot maximum would be omega capital A. Omega is the frequency at which the mass is vibrating, and A is the amplitude of the vibration. Similarly, acceleration would be also maximum at the extreme positions, and its maximum value would be x double dot maximum. It is equal to omega square A. So once we have the amplitude of displacement, so if we multiply that once with omega, the frequency of vibration, we would get the amplitude of the velocity. However, if you multiply that again with omega, omega square a would be the amplitude of the acceleration. Now let's discuss another method by which we could find out the natural frequency of the system. It is known as Rayleigh's method. It is used to determine the natural frequency of the system. But remember that it is applicable only to conservative system. By conservative system, we mean that the law of conservation of energy is used. That is, energy can neither be created nor destroyed, or the total energy of the system remains constant. So it is normally applicable to the system where we are not considering the damping. So if the system is conservative, it has no damping, then we could use the Rayleigh's method. And according to Rayleigh's method, the kinetic energy maximum is equal to potential energy maximum. That is, the maximum kinetic energy and the maximum potential energy of the vibratory system would be equal. We last time we discussed that during vibration, what happens? The kinetic energy changes into potential energy, and the potential energy then changes it back to kinetic energy. The kinetic energy is maximum at the mean position or equilibrium position of the system. However, the potential energy is actually maximum at the extreme positions. So the system would have a maximum kinetic energy and it would have a maximum potential energy. If there is no damping or negligible damping, then these two would be equal to each other. And that is actually the Rayleigh's method. So T maximum is equal to U maximum. Kinetic energy is maximum as we discussed at the static equilibrium position, whereas potential energy would be maximum at the extreme displacement positions. So let's say we have the spring mass system, and this is the equilibrium position, and let's say at this instant the mass is moving in the downward direction, and its displacement is x, and we are actually trying to use the Rayleigh's method in order to determine its natural frequency. So Rayleigh's method is saying that T maximum, that maximum kinetic energy, is equal to maximum potential energy. The equation for the maximum kinetic energy is T maximum is equal to half mv square, but we are finding the maximum kinetic energy, so V would be maximum. So V maximum square. So if the motion or vibration is sinusoidal, then mathematically we could write x of t is equal to a sine omega nt, x dot, differentiating this with respect to time, then x dot would be equal to omega n a cos omega nt. And you could see in this equation that this is actually the coefficient with the cos function. So this is actually the amplitude of the velocity. So amplitude of the velocity is omega n a. So this is the maximum velocity. So plugging that into this equation, so T maximum is equal to 1 by 2 m omega n square a square. So this is the maximum kinetic energy of the system, and it would be available at the equilibrium position or mean position of the system. The potential energy in this case is actually stored in the spring because of the strain that occurs into the spring, and that would be the strain energy. So potential energy would be stored in the spring as the strain energy because of the deformation or displacement of the spring. And the mathematical model for the potential energy is half kx square. So maximum potential energy is half k x maximum square. So we need x maximum for that. And the simple harmonic motion, x of t is equal to a sine omega nt. And here this is the amplitude, and this is the maximum displacement which occurs at the extreme position. So the amplitude of x is equal to capital A, and this is the maximum displacement. So plugging that in this equation, u maximum would be equal to 1 by 2 k a square. So we have now the equation for the maximum potential energy and the equation for the maximum kinetic energy. So plugging that in the Rayleigh's equation. So this is the Rayleigh's equation, putting for maximum kinetic energy, maximum potential energy. A square cancels with a square, 1 by 2 cancels with 1 by 2. So we are actually left over with m omega n square is equal to k, or omega n square is equal to k by m, or omega n is equal to under the root k by m, the circular natural frequency of a spring mass system that we have seen previously with the help of the Newton's method and other methods that we discussed in the previous lectures. So we could also use the Rayleigh method. It is very simple method. Just you have to compute the uh, equation for the maximum kinetic energy and equation for the maximum potential energy. Next, we would discuss the problem, and the problem is compute the natural frequency of a car hitting a bump. So we are interested in finding the natural frequency of the suspension system. This is the suspension system of an automobile. It comprises of a spring and a shock absorber, which is used for damping the vibration. So here you could also see a spring and a shock absorber. And here only a leaf spring is used to damp down the vibration. So we are trying to find out the natural frequency of the suspension system of an automobile with the methods that we have learned up to now. So we have to model it, and we have to use the simplified model. The beauty of the modeling is that this is a real system, very complicated system, um, continuous system, distributed system. But actually, with the modeling, lump parameter modeling, very simply we could find out its, or we could approximate for its fundamental frequency. Experimentally, it is possible, but it's not easy. You need a vibrometer, you need some other equipment, uh, for example, DAC card or oscilloscope, and then you need a vehicle, and you have to mount actually the accelerometer there, and then you took a ride, and when your car hit a bump, then you have to find out its natural frequency. That is also possible. But the beauty of the modeling is that here, just by sitting within 1 minute, we have to come with the answer without any equipment, without any sensor, and without any automobile. So let's discuss that. So let's say we are using a simplified model. As I discussed with you before, that the simplest model in the vibration or in the dynamics is actually the spring mass system. So we are ignoring the shock absorber or damping in the suspension system of the automobile for the sake of simplicity, although it would put error in our modeling or computation or calculation, but that is acceptable. That is acceptable for the ease with which we are obtaining the solution for the complicated problem. So let's assume that the wheel, we are taking the wheel as mass, lump mass, that is m, and we are taking the stiffness of the spring as k. So we have a spring mass system. Now here, this wheel is rotating. At the same time, it could move up and down. And let's say this is a pump. This is a pump. And the vehicle is coming, and then actually this wheel is passing over the bump, and then it would vibrate, and we are trying to find out its natural frequency. The wheel is rotating, let's say at that instant when it is moving over the pump from here to here, the rotation of the wheel is theta. R is the radius of the wheel, m is the mass of the wheel, and j is the mass moment of inertia of the wheel. So here we have two types of motions. One is actually the rotation of the wheel. So because of rotation, we would have rotational kinetic energy, and the other is translatory motion. So because of that translation in the upward direction, we would have the kinetic energy translational. The rotational kinetic energy is half j theta dot square, where j is the mass moment of inertia of this wheel about the axis of rotation. And the kinetic energy translatory or translational, it is equal to half mx dot square. So we have already these two equations. We have to just find, depending upon the modeling, this model and the vibration, we have to just find out theta dot or x dot, and then we have to find out the maximum potential energy. So now, when the vehicle were here at this position, this line actually represents the center, the line traced by the center of the wheel. So the center of the wheel were actually moving over this line. And when the wheel actually reach here and start moving over the bump, then actually what happened, the center start moving in the upward direction, and when it reaches here, the displacement of the center is actually, let's say, x of t is the displacement of the center as it climb over the bump. So let's say this is x of t, r is the radius of the wheel, and during this time when the wheel start moving over the pump up to here, the rotation of the wheel is, let's say, theta. So this angle is theta, this angle is theta, and this is x, and this is r. So if we look here, this is theta, r and x, they are related. X and theta are actually related. Although you see two variables, but only one is independent variable. You could take either theta as independent or x is independent. You could see here that sine theta is actually equal to perpendicular, and the perpendicular is x by the hypotenuse. So sine theta is actually equal to x by r. So they are related. X is equal to r sine theta, or sine theta, as I discussed with you, that sine theta in that small right angle triangle, sine theta is equal to x by r. But if theta is small, then sine theta is actually equal to theta. So x by r is equal to theta, or x is equal to r sine theta. So this is actually the relationship between x and theta. So they are related to each other. So we have actually 1 degree of freedom system. And differentiating this with respect to time, x dot would be equal to r theta dot. So the rotational kinetic energy would be equal to half j, and instead of theta dot, we could take out theta dot from here. Theta dot is actually equal to x dot by r. So x dot square by r square. The total kinetic energy would be the sum of um, rotational kinetic energy and the translation kinetic energy. And total maximum kinetic energy would be equal to half j, and the maximum velocity is omega n a, so whole square by r square, plus this is actually the translation kinetic energy, so half m x dot square x, the maximum velocity is omega n a whole square. Now 1 by 2, taking 1 by 2 common and omega n square a common. So inside the parentheses we would have m plus j r square. Next, we have to find out the maximum potential energy. And the maximum potential energy is actually stored in the spring as strain energy, which is because of the deformation or displacement x, and u is equal to half k x square, and maximum potential energy would be half k. Maximum displacement is a, so a square. So we have this equation for maximum potential energy. Now equating these two, so here we have the maximum kinetic energy, and here we have the maximum potential energy. So equating these two, 1 by 2 would cancel with 1 by 2, and a square would cancel with a square. So here we would have m plus j by r square omega n square is equal to k. And bringing this on the other side of the equation, we would have omega n square is equal to k by m plus j r square, or m omega n is equal to under the root k m plus j by r square. So this is actually the equation or mathematical model for the natural frequency of the suspension system when it would hit a bump. So you could see that here we have a spring mass system, but in this spring mass system, this mass is also rotating, and it would have also effect on the natural frequency of the system. And you could see that previously when we were only taking the spring mass system and only translation motion or translatory motion, so the equation for the natural frequency was omega n is equal to k by m. But here, because of rotation, this term has been added, j by r square. And this term in the denominator of the natural frequency is actually known as the effective mass or total effective mass of the system. Next, we would be talking about the stiffness. Last time we discussed that stiffness is the load required to produce unit deformation in the material, or the force which is required to produce unit deformation inside the material. And stiffness is denoted by K, and it is equal to F by X. K is equal to F by X. So normally the stiffness of the material not only depend upon the material and geometry of the member, but it also depends upon the loading condition and the boundary condition. And here in this coming slides, we would see that how the stiffness actually depends upon the material, the geometry of the member, and the loading condition and the boundary condition. So first we are actually discussing that what is the mathematical model for the stiffness when the mechanical member is in tension or compression. So let's say we have a bar, the length of the bar is L, and the cross section is uniform, and we are subjecting this to either tensile load or compressive load. So what would be its stiffness? And in case of compression and tension mean when it is subjected to a pulling load, and compression means when we subject it to the pushing load. So the stiffness in that case is E A by L. E is the modulus of elasticity, A is the cross-section area of the material, and L is the length of the material. E is modulus of elasticity or Young's modulus. So how we got this equation? We would just uh, go over a few equations that we have developed in the mechanics of material. So when the material or this bar is subjected to tensile loading or compressive loading, so in that case, the normal stress sigma is equal to E epsilon, and the stress, the normal stress is equal to the load P. That load P is either here compressive or tensile. So sigma is equal to P by A. And epsilon, which is strain. Strain is actually the deformation per unit original length in this case. So we have epsilon is equal to delta by L. So plugging for epsilon in this equation and also plugging for the stress, normal stress in this equation. So P by A is equal to E sigma by L. Now here, if you look at this equation, in this equation we have the load, that is force, and we have also the deformation. And stiffness, we define stiffness as load per unit deformation. So rearranging this equation for the load per unit deformation. So load and bringing this delta on the other side. So load per unit deformation is equal to bringing that A on the other side. So we would have EA by L. So P by delta is equal to EA by L. We get actually this equation. And in this equation, this quantity is actually what? It is the stiffness. So putting this as K, so this is actually K, the stiffness. So K is equal to EA by L. So it means that when we have a mechanical member and it is subjected to tension or compression, then in that case, the stiffness of that rod or that member would be K is equal to EA by L. Now, if we look at the equation, it tells us that the uh, stiffness actually depends upon E. E depends upon the material. So means that the stiffness of a component depends upon the material. And A and L, it is related to the geometry. So it means that the stiffness also depends upon the geometry of the material. So from the equation, we conclude that the stiffness depends upon the geometry, and it also depends upon the nature of the material of the member. Next, stiffness element beams in bending. So let's say that we have a beam, one end of the beam is fixed. We have the same rod. Assume that we have the same rod, but now actually we are fixing one end of the rod, same rod having length L, cross section area, and the other end is free. So it is just as a cantilever beam. It is just a cantilever beam, one end fixed, one end free. So, and at the free end, we are applying a transverse load F in the downward direction. And because of that loading, what is happening? The tip of the beam has displaced through distance delta. And in this case, in the cantilever beam, the beam stiffness KB, B stands for beam, the beam stiffness is actually equal to 3 EI by L cube, where E is the modulus of elasticity and I is the second moment of area or area moment of inertia relative to the beam axis. And I is the area moment of inertia, depends upon the cross section of the beam, whether the beam is circular or whether it is rectangular or square or triangular. So you have already studied that in the mechanics of material. So here in this case, the beam stiffness in case of cantilever beam, it will be 3 EI by L cube. How we got that equation? If we have a cantilever beam having length L and it is subjected to load F, then the displacement of the free tip, it is actually equal to FL cube by 3EI. You could find this mathematical model for the tip displacement in any vibration book or in any mechanics of material book. So delta is equal to FL cube by 3 EI. if we look at the equation, in the equation we have delta, that is the displacement, and we have the load. And stiffness is the load per unit displacement or deformation. So just rearranging this equation so that we have the force per unit displacement. So F by L from that equation is equal to 3 EI by L cube, and F by delta is actually stiffness. So here the stiffness KB is equal to 3 EI by L cube. So here again, if we look at the equation, the stiffness depends upon the E, that is the nature of the material of the component, and it depends upon I. I actually is the second moment of area. It depends upon the geometry of the material, geometry of the beam, whether it is rectangular, whether it is circular, whether it is triangular, whether it is square. So it depends upon the geometry of the material and the nature of the bending of the material. And L cube, so L is also related to the geometry of the material. So the equation is telling us that it depends upon the material and geometry. But if we look at the previous equation, we have the same rod. We have the same rod, but now we have fixed one end and the other end is free, and we have subjected it to the transverse loading. The mathematical model for the stiffness has changed. So what does that mean? It means that if you change the boundary condition, now this is the boundary condition. In the previous case, we have at the boundary, we were actually applying the compressive loading or tensile loading. Here, the boundary condition is that this end is fixed and the other end is free. This is the boundary condition. And the loading condition has changed. We have also changed the loading condition. Here, the loading is transverse loading. So meaning that if we change the loading condition, the stiffness of the component would change. If you change the boundary condition, the stiffness of the material would change. If you change the geometry of the material, the stiffness of the material would change. If you change the material of the component, the stiffness of the material would change. We have the same rod of length L, but now again we are changing the boundary condition. We are also fixing the other end. So the other end has been fixed. And so we have changed the boundary conditions. And we are also changing the loading conditions. We are applying the same load F, but now at the midspan, of the beam. And let's say because of that, there is deflection of the beam, and the maximum displacement of the beam is, let's say, delta maximum. The F is equal to K delta maximum. This is the relation, this is the spring force. F is equal to Kx, but here we are using delta maximum. And delta maximum for fixed beam, here we have fixed beam, and the mathematical model for delta maximum for fixed beam is actually equal to FL cube by 192 EI. In this equation we have delta, and in this equation we have F. So just rearranging the equation, so bringing this quantity here and all these quantities on the other side, so we would have F by delta is equal to 192 EI by L cube. And this is what, this is actually the stiffness of this fixed beam. KB is equal to 192 EI by L cube. We have just changed the boundary condition and loading condition. The material is same, the geometry is same, but the stiffness would change. If we have a simply supported beam, now we have a simply supported beam, the loading, the boundary condition has changed. Now we have changed the boundary condition from the previous case. The loading condition is same. The geometry of the component is same. The material is same. The deflection would be a little bit different because now we have a simply supported beam. In that case, delta maximum is equal to FL cube by 48 EI. Rearranging the equation for F by delta maximum, F by delta maximum would be equal to 48 EI by L cube. And this would be the beam stiffness in case of simply supported beam, and it would be 48 EI by L cube. We have just changed the boundary condition. Now we have a simply supported beam, and it has changed the model for the stiffness of the beam. Same rod, we have same rod, length L, same material, but now we are again changing the loading condition and boundary condition. Both ends are free, both ends are free, but we are just subjecting these two ends to a torque. So now we have a case of torsion. We have a case of torsion. We are applying a torque T here, torque T here. And in this case, the torsional stiffness would be equal to Gj by L, where G is the modulus of rigidity, L is the length of the rod, and J is actually the polar area moment. It is the second moment of area in case of actually torsion. So it is known as polar area moment. And for round shafts, actually with diameter d, J is equal to uh, pi d4 by 32. T is equal to kt theta. This is actually the relationship between the loading and the deformation. Kt from here, kt is equal to T by theta. So meaning that in order the torsional stiffness, this is the definition of the torsional stiffness. The torque which is required to produce unit angular deformation. Kt is equal to T by theta. So the torque or the moment which is required to produce unit angular deformation inside the material. So meaning that we have to find T by theta, and that T by theta would be the torsional stiffness. In case of torque, this is the popular torsional formula, ta by rho, that is shear stress by rho. Rho is the distance from the center of the rod. It is equal to T by J is equal to G theta by L. Theta is the twist, modulus of rigidity, length of rod, torque to which the rod is subjected, and polar area moment. Look, if we look at this equation, this part of the equation, that is G by T by J is equal to G theta by L. So here T, you see T and also theta. So rearranging the equation for T by theta is equal to G J by L, and this T by theta is actually the torsional stiffness, KT. So KT is equal to G J by L. So this is actually the stiffness in case of the torque. So now you have seen that the stiffness of the component depends upon the material. Um, it depends upon the Young's modulus of elasticity of material, or modulus of rigidity of the material. It depends upon the geometry of the material. It also depends upon the boundary condition, and it depends upon the loading condition. If you change one in all these four, among four, the stiffness of the component would change. Next, we would be discussing, because in the during modeling, we would come across the problems where we would have a number of springs, and sometimes those springs would be in parallel, sometimes they would be in series. So these coming slides are about that, how to find out the equivalent stiffnesses of these springs when they are in parallel or when they are in series. So first we would take the case where the springs are in parallel. So how to combine stiffness elements. So let's say we have a bar, and to that bar two springs are attached. The other end of the springs are fixed. The stiffness of this spring is K1. Stiffness of this spring is K2. We have applied a force such that the bar remains horizontal. and in that case we are trying to find out the equivalent stiffness. The corresponding equivalent system for these two springs which are in parallel would be K equivalent is the equivalent stiffness, and we are subjecting it to the same load. And let's say that when this load is applied, the displacement of these two springs is x. X is the displacement. Again here x is the displacement of this end of the spring. So for this system, the force F, the spring force, would be K equivalent times X. So the spring force here is K equivalent X. Here, this total force would be taken sum by this force, this spring, and the remaining would be taken by this spring. So F, the force, external force, it is equal to the force taken by spring having stiffness K1 plus the force taken by the second spring having stiffness K2. F1, because the displacement here is x, so F1 is actually equal to K1x. Again, the displacement here, it is x, so in terms of x, the spring force F2 would be K2x. So we have this equation. This F is actually equal to K equivalent X. So here instead of F, we could write down K equivalent X. Now, if we divide this equation throughout by X, at the end we would get K equivalent, it is equal to K1 plus K2. So meaning that if we have springs in parallel, then the equivalent stiffness would be the sum of individual stiffnesses. Next, if we have springs in series, just like this, these two springs are attached to each other, and at this end we are applying a force in the downward direction. And as a result, there is a displacement of this end, and let's say that displacement is x. X1 is actually the displacement in spring having stiffness K1, and X2 is the displacement in spring K2, and the addition of these two would give us actually the total displacement at this end of the spring. So x is equal to x1 plus x2. Here the displacement would be different, however the force throughout the system would be same. And we could see this in the freebird diagram. This is the freebird diagram of the system. We have separated these two springs. These springs are separated, and you could see that at this end we are applying force F. The system is in equilibrium, so the load on that end of the spring would be also F. If this is F, the load on this side of the spring would be in the downward direction in order to cancel this one, because we have cut this here, so that load would be also F. If this load is F, this spring is in equilibrium, so on the other side the force would be F. So the force in this spring is F, also the force in this spring is F. When the springs are in series, so the force throughout the springs would be the same. The displacement would be different. When the springs are in parallel, the displacement in each spring would be same. However, the force in each spring would be different. But that is not the case here. Here the force throughout these springs is same, however displacement is different. The equivalent system for this would be like this, K equivalent, and here we are subjecting it to the force F, and we have the same displacement x. So the spring force here, it is F is equal to K equivalent x. So here x is equal to x1 plus x2, and from the equivalent system, x is from this equation, x is F by K equivalent, and x1 is F by K1, and x2 is F by K2. Now dividing this equation throughout by F. So after doing that, we would have 1 over K equivalent is equal to 1 over K1 plus 1 over K2. So it means that when the springs are in series, then the reciprocal of the equivalent stiffness would be equal to the sum of the reciprocal of the individual stiffnesses. We could rearrange this equation. We could write it more simple form as K equivalent is equal to, by taking LCM here and then inverting the equation. So K equivalent would be equal to K1 K2 by K1 plus K2. So that is the final equation. You could also use that equation or this equation. So when the springs are in parallel, equivalent stiffness would be sum of individual stiffnesses. Whenever the springs are in series, then the reciprocal of the equivalent stiffness would be equal to the sum of the reciprocal of the individual stiffnesses.